In the name of God. Hello, everybody. In this short clip, I'm going to give you an interesting point. In the Krone's primitive machine chapter on our course General Theory of Electrical Machines, we are using the instantaneous power method. As we are using the motoring convention, we say that the electrical power is input, so P input as a function of time equals three components. One of them is PCU, that is loss in the windings. The other one is the rate of change of a stored magnetic field in the inductances, and the other one, which cannot be assigned to anything else rather than the mechanical power output, is the mechanical power output of the Krone's primitive machine. In our derivation, we see that the term which is in proportion to omega m, that is the rotor electrical angular rotational speed, the term in direct proportion to omega m is naturally mechanical power. In this point, I am going to give you that this is not always this simple as you assume. This is for a special case, and we will see when this happens. As a question, I will write a simple question and then do some simple manipulations, and let's see if the mechanical power is in direct proportion to omega mechanic or not. The question is that there is a simple relay. A simple relay has one winding. You can assume that this is the structure. There is a fixed member, and here there is a joint, and this is the moving member, and here there is a single winding. Okay, and as one winding, use the instantaneous power use the instantaneous power method to obtain a relation for the electromechanical torque, we presumably know the answer. You can use the energy and co-energy method, and you know that electromechanical torque is plus round of W prime field, which is a function of there is just one current, so I don't use a subscript I and theta. 2 root theta I assumed constant, and you know that the co-energy is 1/2 Li2, so the correct answer should be 1/2 I2 round L to round of theta. But I don't want to use this method. This is not the instantaneous power method. This is the co-energy method. So let's start by the second method, which is requested in this example. I use the instantaneous power method, the electrical input power, P elect input, as a function of time is vt/it, and vt is d to dt of lambda t, and so it's d to dt of li. I don't use t's to make my writing more compact, and this is L di to dt plus I dl to dt. Of course, you know, if this is a matrix, you cannot interchange the orders, but here we are dealing with the scalars. And I dl to dt, dl to dt is dl to d theta into d theta to dt, and you know that d theta to dt is omega m. Here we are not dealing with a machine which can have more than two pairs or one pole pair, so omega m and omega mechanicus are identical, so we do not confuse. Let's write P electric input is L di to dt into I plus I2 dl to d theta into omega m. And of course you can assume that there is a resistance for the winding, so here vt is ri plus this, so let's add ri plus this, ri plus yes, no problem, and here we will have ri2 plus this. Now concentrate more. If you assume that the term corresponding to mechanical power is this term, then you will write P mechanical is this, and this is torque into omega, torque into omega m, this is torque into omega m, then torque will become I2 dl to d theta. But let's see, the correct answer is not I2 d or round L round T, it is 1 plus 2. What's the problem? The problem is that we did not take into account if the rate of change of magnetic field can have omega m or not. This is the interesting point, and I will explain in detail. See, Wf is 1 by 2 into Li2. If there is a Cron's primitive machine, then the inductance is a constant, and under these conditions, if L is constant, then the rate of change of the energy stored in the inductor or inductors, in the case of multi-coils, we say inductors, it will be for one coil, if there is one inductance, it will be simply 1 by 2 L di to dt, which will be Li di to dt. But the interesting point is that if L can also be a function which is not constant, then dWf to dt will be 1 by 2 L di to dt plus 1 by 2 I2 dl to dt. And let's manipulate a little bit. If L is f theta, which is the case for this simple example, in this simple example I have drawn, L is not constant, so please be careful. Here dWf to dt is 1 by 2 L di to dt. Let's write a simplified version. That is just Li di to dt plus 1 by 2 I2 dl to d theta into omega mechanici. This is something which is very interesting, really an interesting point. Here also you have omega mechanici, but this is not correspondent to the mechanical power. So for this simple example, P electrical input is Ri2 plus. What is the part, the share of dWf to dt is Li di to dt plus, here Li di to dt plus 1 by 2 I2 dl to theta. So half of this third term is not assigned to mechanical power. Half of it is plus this is assigned to the rate of change of the magnetic field, and so P mechanical is 1 by 2 I2 dl to d theta into omega mechanici, and so the electromagnetic torque will have a correct coefficient 1 by 2. This is not correct. This is incorrect. So the correct derivation takes into account that there can be terms having omega mechanical as a coefficient but not assigned to mechanical power. Here I have detailed the derivation. In case L or L's are constant, as is the case for the Crohn's primitive machine, then you can say that every term which has omega mechanic is corresponding to mechanical power. But for several situations, like this simple example, this is not the case. Thank you for your attention.